In this lecture, we are going to discuss about Cauchy theorem. First is a statement of the theorem. Let D be simply connected region, and FZ be single valued continuously differentiable function, continuously differentiable function on D, that is f that z exists and continuous at each point of D, then integral C f z dz is equal to 0, where C is any closed contour containing D. Here D is a simply connected region, that is region without hole. If we draw a curve in D, it will completely lies inside the D. And fz be a single value continuously differentiable function, that is fz exists and continuous at each point of D, then the integral over C fz dz is equal to 0. So C is my closed contour, that is contour whose initial and terminal point coincide, and contour is a finite chain of regular arc are those whose in regular arc are those for which f dash z is not equal to 0. Now let us prove this theorem. Proof: we know the relation between complex integral and line integral is fz dz is equal to fz is written in the form I u plus ib and c, and dz will be my of this form if z is my x plus I y, x plus I y, integral c u dx minus b dy. This is the real part and this is the imaginary part. By using the property of complex integral, I can write this one. So put this equation 1. To prove this theorem, we use Green theorem for plane. According to Green theorem, so write, to prove this theorem, we shall use Green theorem for plane. Which stated states that Green theorem is a theorem which gives the relations between line integral and the surface integral, that is single integral and double integral. For that, we need the function need to satisfy this criteria. If p x y, q x y, del q by del y, del p by del y are all continuous function, continuous function, continuous function of x and y in a domain D, in a domain D, and C is closed contour, C is closed contour, closed contour contained in D, contained in D, then integral, line integral p dx plus q dy is equal to d del q. This is x, okay, this is x, del q by del x minus del p by del y dx dy. We will use the statement of the Green theorem. We are not going to prove this. The here fz is analytic, so fz exists and continuous. So u, v and its partial derivative ux, vx all are continuous, exists and continuous. So it satisfies all the condition of the statement of Green theorem. So we can apply this line integral and double integral relation to this equation 1. So right, since fz is analytic in D, so fx exists and fx equal to ux plus I bx, and this is equal to by minus I ux, that is ux is by and minus bx is ux. By using CR equation, since fz is continuous, so all the partial derivative derivative u v e u x u y b x b y exist and continuous in D. Thus all the condition of Green theorem satisfies, therefore right hand side of 1 can be written as, what is the right hand side one? What is the right hand side of 1? That is integral u dx minus b dy. Integral u dx minus b dy. See. Double integral d, by using Green theorem, I can write here according to Green theorem, if the coefficient of dy is written first with x partial differentiation with respect to x, and p written in the second with partial differentiation with y. So we can write this, that is coefficient of del x minus p minus del u by del y dx dy, and this is equal to double integral d, and this is minus del v by del x minus del u by del y dx dy. This is equal to d. Here in place of minus del vx, we can write del u del y by using CR equation, del u del y dx dy. So write using CR equation. Using CR equation. So this minus this will be 0 and this part will be my 0. This implies C u dx minus b dy is equal to 0. Integral C, then second part of 1, right hand side of 1, p dx u dy. v dx v dx plus u dy is equal to integral of d. The here according to the Green theorem, second term written first with respect to partial derivative of x, del u del x minus del v del y dx by dy. This is equal to d del u del x is equal to del v del y minus del v del y by using CR equation, that is Cauchy-Riemann equation, using CR equation, and this is equal to 0. We have seen the both the part of the right hand side of 1 is 0, therefore 1 becomes therefore 1 becomes therefore 1 becomes integral fz dz is equal to 0. Integral over c fz ds fz dz is equal to 0. Hence the theorem proved. With that, I would like to conclude. Remaining will be in the next lecture.